Hello, this is my COVID-19 exam replacement video 5-2A Quantitative Genetics Decreasing Cattle Dog Tail Size. The prompt required us to pick an organism with a trait that has phenotypical variation and show how breeding the fringe individuals will change the mean of this trait in future generations. Our target organism will be an Australian cattle dog, and the variable feature will be the tail length. For a working dog, a long tail increases the risk of injury while herding, but tail docking is not without risks. So using the methods provided in this course, we'll see what happens to the mean tail length if we breed the bottom 10% of our population. The chosen mean is 18 inches, with a standard deviation from the mean of 2 inches. Two other pieces of information given by the prompt are the values for the broad sense and the realized heritability, which are 0.85 and 0.67 respectively. The value for broad sense heritability shows that 85% of trait variation in the parental population is due to genetic influence. The narrow sense heritability, on the other hand, is the value that represents the ratio of the additive component over the phenotypical variation. This value represents how readily the parental genome can influence a phenotype disregarding the dominance effect. Next, we move our attention to the original population tail distribution curve. This histogram is a graphical representation of our population given standard distribution. The mean and the standard deviation are both labeled on the curve, as well as three other values, the first being the truncation point, x sub t. This term represents the max tail length of the bottom 10% of the parental population, providing breeders a cutoff point. It can be found by adding the mean to the product of the standardized selection point, z, and the standard deviation. For our problem, the table tells us that z for the bottom 10% is negative 1.282, showing that the longest tail in the selected population will be 15.44 inches. The next value we need to determine is the selection differential S. This is the product of the standard deviation and the selection intensity, which is another constant depending on the percentage. This value of S tells us where on the curve the mean of the selected parents, x sub S, will be. We see in this case that the value for S is negative 3.51, making the selected mean 14.49 inches. Finally, we move to the progeny histogram in order to find the mean tail length of the offspring. To find this value, we must use the selection differential and the realized heritability. The multiplication of these two values gives us a decrease in tail size of 2.35 inches, making the mean tail length of the progeny 15.65 inches. But what would happen if we continue this trend indefinitely? Well, surprisingly, a mass selection of cattle dogs for tail length has already occurred. The breed stumpy-tailed cattle dog is a result of this very selection process, showing that this gene drift to the point of the desired working trait is possible. The breed during this transition became taller and more narrow, showing pleiotropic connections between these other two characteristics. However, even though selective breeding achieved a nub, the tail length likely could not be brought to zero. It is safe to assume that the closer we get to zero, the greater the risk of sterile or fatal phenotypes, pointing to a biological limit on gene drift due to selective breeding. These are my references. Thank you for watching.